Hey everyone, I'm gonna do work out a Hardy-Weinberg problem because, but not just any Hardy-Weinberg problem, a chi-squared problem dealing with Hardy-Weinberg. And when these two concepts come together, they can be a bit confusing. So I just want to clarify some stuff. And there's some extra math involved that you might not have seen before, but it's okay. We'll go through it just because it's more logic-based. So if you look at our formula chart here, we have our Hardy-Weinberg equations, and I just want to clarify those real quick and apply some, or set some conventions that I'm going to be using in this video. So just to make sure that it's clear. So we have P plus Q equals 1, which we know. And then if we just square these, square both sides to square the equation, we'll get P squared plus 2PQ plus Q squared equals 1. It's very important we understand what this fundamentally means, because otherwise the rest of this problem doesn't make sense. So P, of course, this is told, they actually tell you in the problem, it's in the formula chart itself, but P is basically the frequency of A, the dominant allele. I'm going to call that A in this video. Q is the frequency of little a, the recessive allele. And then P squared is the frequency of the genotype homozygous dominant. 2PQ is the frequency of the heterozygous big A, little a. And then Q squared is the frequency of the homozygous recessive little a, little a. Okay, hopefully that makes sense. That's the very basic part. We should know that, which is good. Now, say hypothetically, let's just say in a problem that they give us, so given, I'll just say given here, that they give us the phenotypes, they give us the genotype, and they give us the observed. Now, for my own sake, I'm going to put an expected column on here because we don't know that yet. And this is where the challenge comes. Usually when we're dealing with Hardy-Weinberg, we don't have an expected, so we need to come up with that expected. And I'll show you how to come up with that. But let's just say, hypothetically, we have a big phenotype, and the genotype for that is big A, a medium phenotype, which is big A, little a, and then a small phenotype, which is little a. And then, of course, just for my own sake again, I'm going to make a total column here, or total row, I mean, just so we can see. Now, hypothetically, let's just say that this is 75. Notice how I'm using the word hypothetically. 75, this is going to be 15, and this is going to be 10. So let's just say that the total is 100 here, because we can add these up and get 100. Now, here's where the expected numbers comes in. What you have to realize is, since there's 100 individuals total, the total number of alleles, remember, alleles means how many big A's, little a's all combined together. The number of alleles, here, I'll write this here. Total number of alleles is 2 times the number of individuals. And I'm not going to use my calculator for this. This is just going to be 200, right? So because each individual has 2 alleles, right? So if I myself, I might have a big A. Someone over there might have big A, little a. So each of us has 2 alleles. 2 times 100 people means there's 200 alleles, okay? That's very important. Now, we need to find P and Q. And the reason why is we're going to get to expected. Now, to get to expected, essentially what we're trying to find, remember, big A is P squared, right? So we're trying to find P squared times 100, because P squared is a frequency and we have 100 individuals. So the expected number for big A is going to be P squared times the number of individuals. If you want a generic formula, that's what you're going to write. You're going to write P squared times the number of individuals, which is this total number here, this 100. So in this case, it's going to be 100 P squared, and we'll find out what that value is, okay? And here, we're going to get 2PQ, right? Because this is the medium. And as we see here, that's 2PQ times the number of individuals, which in this case is 100. So 100 2PQ. That's 1,000 too. It should be 200 PQ in this case, because we have the 2 out front and the 100. So our coefficient is 200. PQ equals, we'll figure that out. And then finally, we need to find Q squared times the number of individuals to get our expected for little a. This is going to be 100 Q squared, okay? And that's what we're going to figure out. of course, our expected here should also total to 100. If that's not the case, then we've done something wrong. Now, here's where the magic comes in. We need to find P and Q. Now, I'm going to give you a formula, but I'm going to walk you through it. So P is equal to the number of big A's, right? By definition, it's the frequency of big A. So it's the number of big A's over the total number of alleles. So total number alleles. Well, we already figured out the total number of alleles. In this case, it's 200. So we're going to put 200 in the denominator. Now, this is what might be a little bit unintuitive, but just walk with me here. If we have the number of A's, look here. Where can we get A's? The only possibilities of A's are big A, or big A, little a. However, this is very important. You multiply the number of AA's by 2, the big A by 2, because we're looking at each individual allele. And AA, the genotype AA, big A, has 2 big A's. So we multiply the number of AA's by 2, and we add that to the number of big A, because the big A, is just contributing 1 big A. And we're only concerned about the number of big A's here. So 2 big A plus big A, over 200. So this is going to be 2 times 75, 2 times, so this is your formula if you want it. It's the number of A's over total number, or you can remember it as 2 big A plus big A, over number of alleles. Okay? So this is going to be 2 times, and I'll give you an even more generalized formula at the very end. But I want to really walk through this whole thing because it makes more sense if we do that. So here it would be 2 times 75 plus big A, which is 15, over 200. And I'm going to just put that in my calculator here. I know the brightness is pretty big, so let's just put that in. 2 times 75 plus 15, all of that over 200. And if I get it in as a decimal, it's 0.825. I don't know if you can see that, but there it is. So that's 0.825. Okay, now we're going to find Q. By the same logic here, it's the number of little a's over the total number of alleles. Okay, so that's going to equal 2 times, this time little a, plus big A, because remember, the small genotype, the little a is contributing 2 little a's, and then the heterozygous genotype, big A, is only contributing 1. And of course, we divide by 200 since that's the total number. And that's going to equal 2 times 10 plus 15 over 200. If we do that, we get, once again, I'm going to put that in my calculator, 2 times 10 plus 15 all over 200, and we get 0.175. Now, how can I check? Remember, the first Hardy-Weinberg equation is P plus Q equals 1. So if I add these two together, 0.825 plus 0.175, I better get 1. And that's the case. You can check that out. If you're not convinced, 0.825 plus 0.175, it indeed does equal 1. If it didn't equal 1, that means you probably messed up on your math somewhere here. But no worries, but it's okay. Now that we have P and Q, we can actually figure out the expected numbers because we have P and Q. So remember, expected number of big A is P squared times the number of individuals, because it's P squared, the frequency of big A, times the total, okay? So we do P squared, P was 0.825, we square that, and we multiply that by 100, since we have 100 people total, and we get 68.0, I'm gonna round to 0.6 just because I don't have space, but ideally just store these numbers in your calculator. For number of heterozygous, we do 2PQ times the number of individuals. So we have 2 times P, P is 0.825, times Q is 0.175, times 100. And we get 28.875. 28.87, all right, I was able to squish it in there. Once again, just save these numbers in your calculator. And finally, we have Q squared times 100 for the number of individuals with little a. So we're gonna do Q, which is 0.175 squared times 100, and we get 3.0625. Once again, I'm just going to round to 3.06. Now is where the chi-squared happens, okay? So for chi-squared, I'm just going to do this directly in my calculator. You can actually go to the equation sheet for this. Chi-squared, as you can see, is the sum of observed minus expected squared, quantity squared, over expected. So I'm just going to go to my calculator here and directly put this in. Observed is 75 minus expected is 68.06 as we calculated. So I'm just going to directly take that number and plug it in there. Squared over expected, which is once again the, oh, I messed up there. Sorry about that. And here we want the 68.0625. So that's the first thing. Then we add the second observed, 15 minus that number squared. So 15 minus the 28.875 squared, quantity squared, over 28.875. And finally, we add the, so that was for the heterozygous genotype, by the way. And finally, we do it for the small, so the homozygous recessive genotype, which is 10 minus, oh, sorry, I should have put a parenthesis there. 10 minus, what is the number here again? 3.06. So I'm going to take 3.0625 squared over 3.0625. And look at that. You get your chi-squared in this case, which is chi-squared 23.09 approximately. Okay? So you get 23.09. Now, if we were doing chi-squared analysis, we need to check whether this number is greater than the critical value. If it's greater than the critical value, we can reject our null hypothesis and conclude with a certain confidence level that our alternative hypothesis is acceptable. So if we look at the degrees of freedom, now this is where the table comes in. But remember, this is Hardy-Weinberg. So even though we have 3 outcomes, the degrees of freedom is not 3 minus 1 equals 2. The degrees of freedom is not 2. In Hardy-Weinberg, the degrees of freedom is 1. Why? Well, because if I know what P is, I can immediately figure out what Q is. Or if I know what Q squared is, I can figure out Q and P and 2PQ. So what the thing to remember in Hardy-Weinberg is if I know one of them, I can figure out the other ones. Because if they give me P squared, I can figure out P, and then I can figure out Q, and then I can figure out 2PQ and everything, really. So with Hardy-Weinberg, there's only one degree of freedom in a case like this. So the degree of freedom is 1. So I'm going to go to degree DF, degrees of freedom for 1. And let's say I have a 95% confidence interval, which is the p-value of 0.05. 3.84 is the critical value. And now I check. Is 23.09 greater than 3.84? It most certainly is. And therefore, we can say that we can reject the null hypothesis with statistical significance of a confidence interval of 95%. Okay, so I'm going to erase this real quick and just write some general notes. This is how to work out this problem in detail. Here, let me take a screenshot of this so I can share this image just with y'all. Okay. All right, now I'm going to erase this, and then I'll write out some of the general formulas we figured out. Okay. So for expected, okay? So for expected, actually let's start with something a little bit more basic. So let's start with what P and Q is. When you have Hardy-Weinberg, how do we figure out P and Q? P is equal to 2 times the number of people. Oh, I'm so sorry. Let me start off even more basic. Total number of alleles. That's the first equation we started with. Total number of alleles is 2 times the number of individuals. Hopefully that makes sense how I explained it, because if there's 100 people, there's 200 alleles because each of them has 2 alleles. Now, how do we figure out what P is? Well, P is going to be the total number of A's, the dominant alleles, over the total number of alleles. Okay? And if you're looking for a formula for that, well, that's going to equal 2 times the number of big A, I'll say this, 2 times number of individuals with big A, plus the number of individuals with big A, little a, because they contribute just 1 big A, and these people contribute 2 big A's. That's why we multiply by 2, over the total number of alleles. And that's equal to, if you apply this formula, this is 2 times the number of AA plus the number of big A, little a, over 2 times the number of individuals. Okay? Now to find Q, we have number of little a's over total number of alleles, and that's equal to, similarly, it's the same exact, essentially the same exact concept, 2 times number of individuals of little a plus number of individuals of big A little a, same logic here, over 2 times the number of individuals, 2 times the number of alleles, and by extension, I'm just going to leave it as that, 2 times the number of individuals, because that's the total number of alleles. Same, I just directly went there. So now, the other important thing for Hardy-Weinberg chi-squared problems is you need the expected, okay? The expected values for big A is going to be p squared, because that's the homozygous dominant frequency, times the number of individuals, okay? Big A little a, heterozygous, is going to be 2pq times the number of individuals. And finally, little a, the homozygous recessive, is going to be q squared times the number of individuals, okay? And finally, what you need to remember, the degrees of freedom, df, is not going to be 2, it's going to be 1 in this case, because as soon as you know one of these, you can know all of the other ones, okay? So I'm going to take another screenshot of this, just so we have a nice summary up here. Okay, all right. And that's pretty much it. Hopefully that explains this, that clears this up, and good luck.